This is the assignment 601 work problem set. We're going to work through the questions and hopefully answer any questions that you have. The first question says, choose all situations below in which no work is done. And so here you're looking at a series of scenarios, and you can pick one answer, more than one answer, all of the answers, as long as you are selecting something where there is no work being done. The choices that we have are: a teenager pushes a lawnmower across the lawn at a constant speed. The second one says a cart slides along the floor frictionlessly. The third one says a jogger runs up the stairs at a constant speed. The fourth one says a weightlifter holds weights in an overhead position. The fifth one, a weightlifter raises weights from the ground to an overhead position, and then a child pushes against a wall. In order for work to be done, there are a couple criteria that have to be met. The first of which is that you have to have a force acting on an object, and that force needs to, at least some component of that force needs to be parallel to the direction of displacement. So the force can be causing the displacement of the object by, for example, pushing something forward. Your force is forward and it moves forward. Or you can have a force that opposes the direction of motion of an object, like friction can do work on an object in order to slow it down. And so here we're looking for situations where there is no work being done. You're not going to have any work done if you don't have any displacement in the same direction as the force that's been applied, or at least some component of that force, because force is at an angle. There is a component of the force that would be doing the work. So if you don't have any motion, any displacement at all, then you can't have any work. Obviously, if you don't have any force, then you can't have any work. Whenever you look at the equation for work, it is force times displacement, or at least that displacement that is in the same direction. And so we're looking for situations where our force is zero or where our displacement is zero, because those will be situations where there's no work being done. So a teenager pushing a lawnmower across the lawn at constant speed would be work. You would have somebody pushing something, that object is now moving and therefore is being displaced. Again, the equation that we'd be working with work is that our work is equal to our force times our displacement. And again, it's only that component of the displacement in the same direction, and so you'll often see it written like this, because this is the component of this whenever you do the trig, like we talked about in class. Or you may see it written like this, FD cosine theta. It's in distance instead of displacement for delta x, but whenever you're dealing with something where there is only motion in one direction, then your distance and displacement are the same value anyway, and so they sometimes are used interchangeably here. So again, we're looking for a zero here or here. Or, of course, if your cosine theta is zero, then that would also be a situation where you have no work. But this one right here, teenager pushing, that is work. A cart slides along the floor frictionlessly. There's no friction here, and so there's no force from friction. It doesn't mention anybody pushing that cart. It just says that it's sliding along the floor, and so there would be no force being applied to that cart, and therefore there'd be no work being done here. The next one, jogger runs up the stairs at a constant speed. If you are running upward, you are using a force to lift your own body weight, and you're lifting yourself up by whatever the height is that you climb to. And so this would be an example of work. A weightlifter holds weights in an overhead position is not work. If you're holding something in a position, then you're not causing displacement of that object. And so if your displacement is zero, of course your work is zero. A weightlifter raises weights from the ground to an overhead position. This is a situation where there is a force and it is causing displacement, and they're both in the same direction, they're both upward, and so that would be an example of work. A child pushes against a wall. We're going to assume here that the child can't actually move the wall, and so we're going to select that answer as well. Question number 2 says, in each of the situations below, two or more forces act on the object or person described. Net work is described as the total work done by all of the forces acting on the object. Choose all situations in which no net work is done. So again, same situation here. When we're talking about work, we're looking for situations where either there's no force being applied, there's no displacement of the object, they don't move it, or that force is being applied perpendicular, because whenever you take the cosine of that, you're going to get 0. Your force has to be parallel. But because it's talking about net work, you could also have situations here where you have one person or object pushing in one direction and another person or object pushing in the opposite direction, where those are canceling each other out. So if you have a situation where you have a net force of 0, then of course that would also be a situation where you have no net work. So this first one says a shopping cart is accelerated from rest to 3 meters per second. Of course, if we see acceleration, we know that we have net force, and therefore we will have net work. We're looking for situations with no net work, so we're not going to select this because this would have net work being done. The second one says a cart slides down a frictionless ramp. If this cart is sliding down a frictionless ramp, of course, there is no force of friction. However, if something is sliding down a ramp, then you know that the reason that it's going down that ramp is because gravity, or the Earth's gravitational field, is applying force to that object, or in this case, that cart. And so you can have work done on an object by gravity, which is exactly what this would be. There is no counter force due to friction. It's frictionless. And so that would be your only net force, would be the component of gravity that's in the parallel to the ramp. And so this would be a situation where you do have net work being done by Earth's gravitational field. So we can't select that. The next one says a marathoner maintains a speed of 6 meters per second in a race. If you have constant speed, then you're going to have a situation where you have a net force of 0. And if you have a net force of 0, according to this equation, if this is F net, then of course you would have 0 work. And so any situation where you have constant velocity is going to be a situation in which there is 0 net work. A Toyota accelerates from 0 to 60 in 10 seconds. Again, if you have acceleration, you have net force, and therefore you have net work. So we will not be selecting that one. The next one says a textbook is raised very slowly from ground to a table. Again, you have force that's being applied here, and it's being applied in the direction of the displacement from the ground to the table. And so that one, you have at least initially acceleration as it's lifted from the ground. But it's talking here about as it's raised, so the wording's a little bit tricky. I don't know if this is meaning to imply that it's at constant velocity, but if so, we would want to select this as well if we have constant velocity here. And then we have a lawnmower is pushed at constant speed, so again, same thing. Yeah, I think it wants us to select that one there, it does. Okay, so a textbook is raised very slowly from the ground to the table. I don't like this wording particularly, but it is implying here that it's moving at a constant rate. All right, the next question says, calculate the work done on a crate pushed 3.4 meters up along a ramp as in the figure below. And it says the man exerts a force of 440 newtons on the crate parallel to the ramp, and the crate moves at a constant speed. The work done by the man on the crate is blank joules. And so we're going to be filling this in. We know that we have the force that the man is exerting, 440 newtons, and we have the displacement of the crate along the surface of the ramp. And so because we know both the force and the displacement, we can just use our work equation, and since it's parallel to the ramp, then all of that force is in that same direction. And so then you're in a situation where you're doing a cosine of 0, which of course is 1. So you don't really need this part. If your entire force is parallel to your displacement, you can simply multiply the values. Again, right there, cosine of 0 is 1. So if you want to plug in 0 degrees, since it is along the same axis, you can. But we're just going to take that force, that 440, and we're going to multiply it by that 3.4 meters. And when we multiply our force there by our displacement, 440 times 3.4, we end up with an answer of 1,496. And our units here are Newton times meters, Newton meters, which is the same thing as a joule. And so let's go ahead and type in our answer, 1,496 joules. Question number 4 says, a shopper pushes a grocery cart 21.6 meters at constant speed on level ground. If the shopper pushes with 18 newtons of force, how much work is done by the shopper? Again, the equation for work is going to be force times displacement times cosine of theta. Again, if it's not at an angle, you can really ignore this part. Okay, because you can see here I'm not at an angle, I'm just pushing it on level ground. And so it's just going to be the force times the displacement, because my angle here, if it's in the same direction as the displacement, that's an angle of 0, and cosine of 0 is 1. So again, if it's not at an angle, you really don't need to pay attention to this part. You just need to multiply, in that case, the force times the displacement. Okay, when we're not at an angle, it's a little bit easier. So here, our force is 18 newtons. The displacement is 21.6. Again, both of those numbers come from the question above. And so if I multiply 18 times 21.6, then I'm going to get 388.8. And again, that's newtons times meters, Newton meters or joules. So let's go ahead and type it in. 388.8. What is the net work done on the grocery cart by all of the forces acting on it? So this is just the work done by the shopper. And in order for me to find that, I use the shopper's force. But if it asks me about the net work rather than the work done by one of the actors in the situation, one of the different objects interacting, then I need to take a look at what forces are present. And it's a good idea to start with a free body diagram. I'm going to go ahead and say that my applied force from my shopper is this way. So that's going to be my applied force. That's that 18 newtons that we just looked at. I know that I have Fg and I know that I have Fn. Those are not going to be really involved with any of the motion of this cart because those are just going to be equal and opposite since my cart is simply moving across level ground. But it does say in the question that it's moving across level ground at a constant speed, and it says those words right here. And when you see constant speed, that should tell you that you have balanced forces. So this force here and this force here need to be equal and opposite to each other as well. And so it's probably friction. It doesn't actually say. We just know that it's moving at constant speed. So there's some other force that's countering this force here. So I'm assuming it's probably friction, but again, it could be a child dragging the cart backward or something, or trying to drag it backward, where you have an equal amount of force here that's causing you to move at a constant speed. Whatever the cause of that, the net force in this situation is 0. Because it says constant speed, I have to have a net force of 0 newtons. And if I have a net force of 0 newtons, then the net work is 0. Because again, this is the work done by the shopper, and it's due to the force done by the shopper. If we're looking for the net work, then our equation looks exactly the same, except now this is the net work, and it's done by the net force times the displacement. And so, of course, if my net force is 0, my net work will also be 0. Friction is one way to reconcile the results in A and B above. That's what I mentioned. This force right here could very well be friction. How much work is done by friction? So it's telling us, hey, let's call this friction. Okay, how much work is done by friction? Be mindful of the direction. So again, these have to be equal and opposite. And so if those are equal and opposite, then the forces, or not the forces, the work done by those forces are also equal and opposite. So if the shopper does 388.8 joules of work, then friction does negative 388.8 joules of work, so that you end up with a net work of 0. Question 5. A weightlifter lifts a height of 1.4 meters directly upward, slowly at a constant rate. If the weight weighs 400 newtons, how much work is done by the weightlifter? Okay, so again, it's asking us for the work done by the weightlifter. In order for us to find the work done by the weightlifter, we need the equation. Again, work is force times displacement. And if it's the work done by the weightlifter, then it's the force applied by the weightlifter. Those need to be consistent with one another. So I know that the weight has a weight of 400 newtons, and therefore that's the force that has to be applied in order to lift that, is we have to have 400 newtons of force, and that 400 newtons is being applied as the weightlifter lifts that to a height, which would be my displacement in this case, of 1.4 meters. So if they give you the weight of something and they're asking you how much work is done when you lift that weight from the ground, you're going to take the weight in newtons and you're going to multiply it by the height to which you lift it. And that's going to give you the amount of work done, in this case by the weightlifter. So again, that's going to be 400 times 1.4, which is going to give us an answer of 560 joules. The weightlifter would be applying this force as he's lifting it. If this is the weight that's being lifted, this is the applied force from the weightlifter. And the displacement is also upward, and because they're in the same direction, I know that the work done is going to be a positive amount of work. And so the weightlifter does 560 joules of work. A motorist runs out of gas on a level road 210 meters from a gas station. The driver pushes the 950 kilogram car to the gas station. If a 270 Newton force is required to keep the car moving, how much work does the driver do? So again, same thing. We're looking at our equation for work. Let me get paper so that we can write on it. Okay, and so we're going to say again that work is equal to force times displacement, and in this case there's nothing here at an angle, so there's no cosine theta to worry about. We're going to say that the motorist, the driver, is pushing with a force of 270 newtons. That's the force here. The displacement, how far he is pushing that, is 210 meters, and so that's it. The mass that they provide us, the 950 kilograms, is just extra information in this question. We don't need that value in order to get our answer. We're just going to multiply the applied force, 270, by the distance that he is applying that force, 210. And when we multiply those numbers, we get this value right here, 56,700. And our units for work will be joules. Oops, yeah. And so that's how you answer this question. So again, don't get thrown off by extra information. All right, here we have a force displacement graph, and it says this is a graph of the force done on a moving object as a function of distance. How much work is done on the object in the first 12 meters? Again, if you have a scenario and you look at the axes on your graph, force and displacement in this case, and if your equation for work, which is what you're trying to find, tells you that you are multiplying your x and y axes, because that's what you're doing. Here's force, here's displacement. My equation is force times displacement. If you are multiplying your y times your x axis, you need to find the area under the curve, or area under the data points. In this case, it's a trapezoid. But you're going to have to find that area, and it just wants the first 12 meters, so we're actually only looking at the triangle right here for the first 12 meters, but the area is the work. If you have a force displacement graph, area is work because you are multiplying force times displacement to get work. That's area. It's like length times width, except it's the average force in this case because the force is changing, so that's why we use the area equation. So 1/2 base times height is going to give us, in this case, work, because that is going to be average force times displacement. Whenever we get half of that total force, half of 42, according to this graph, is 21 times the displacement there is 12. So that becomes average force times displacement, which of course is going to give us our work. but that's what this is, 1/2 base times height. Okay, so I did 1/2 of 42, and then I multiply it by the 12. So 21 times 12 gives us 252, and our unit, of course, is joules. How much work is done on the object from 12 to 24 meters? Well, from 12 to 24 meters, we have a constant force of 42 newtons being applied, and it's being applied from 12 to 24 meters, so that is applied over a total displacement here of 12 meters. So now we don't have to do the average. Now it's the area of this rectangle, and it's going to be 42 times 12, which is 504 joules. So again, if you have a force displacement graph and you were trying to find work, you need to find area. And it's always the area between the x-axis and wherever your data points are. So in this case, it's a triangle for the first 12 and then a rectangle after that. All right, this is question number 8. It says a woodchuck uses a force of 3.10 newtons to push a pebble across the ground and does 6.60 joules of work on the pebble. How far did the pebble move during this process? Again, it's the same equation. We're just giving you different pieces of information now. Now they're telling you the work that's being done. So the work that's being done here is 6.60, and we're going to set that equal to force times displacement. They gave us a force, 3.10, and we're going to solve for displacement. That's what I want to know, how far. So all you're doing is dividing both sides by 3.10 in order to isolate that variable and get your answer. So 6.6 divided by 3.1 is 2.129. And you can round it more than that if you want, but I'm going to round it right there. Question number 9 says a man is pushing his 1,180 kilogram car with a horizontal force of 260 newtons. The car moves forward 20 meters at a constant velocity of 0.8 meters per second. How much work is done by each of these forces? Okay, so we have here a situation where we have different forces, different displacement, or rather really just one displacement, but a bunch of different information. So I know, first of all, let's talk about the force of gravity and the normal force. Let's get those out of the way first. Because this car moves forward, okay? It moves forward 20 meters. It doesn't have any vertical motion. So it's moving in this direction, and so this normal force is at 90 degrees from that. Okay, well again, this is our equation for work. Work is force times displacement, but it's only the component of displacement that's parallel to the force. Okay, your displacement needs to be in the same direction or along the same axis. Again, that's why we write it like this. It's actually that dot product of force and displacement. And so again, if you take that normal force, it's at 90 degrees from the direction of the applied force, that pushing force right here. Okay, and so if you do that, and let's get us in degree mode. Okay, cosine of 90 is 0. So again, if you have a force that is perpendicular to the direction of the displacement, those forces do no work. There is 0 joules of work done by the normal force. There are also 0 joules of work done by the gravitational force, because both of those two forces are perpendicular. They are 90 degrees from the direction of the displacement. Okay, and so if they are 90 degrees from that direction of displacement, there is no work being done by either of them. Now, when we look at the other two forces, his pushing force and that frictional force, those are, well, in the case of the pushing force, 0 degrees, okay, and then in the case of friction, 180 degrees, because it's exactly opposite the direction. But in either case, we can calculate the amount of work being done by these forces, and there will be work done because we have displacement, okay, and we have a force that is causing or opposing that displacement. And so whenever we look at these, let's go ahead and do the pushing force first. His pushing force, again, I don't care about the mass for this, unless they wanted me to actually calculate like force of friction. They could do that where I have to use the mass to get Fg and Fn and then use a coefficient in order to figure out my force of friction. That's possible, but that's not what they're asking me to do here. In fact, they tell me what the force is. So they tell me that we're pushing this car with a force of 260 newtons. We don't need the mass. It's just extra information. I know that they're pushing it with this amount of force for 20 meters. So there's my force, there's my displacement. Again, if you want, you can type in times cosine of 0, because again, it's in the same direction. There's the direction of my force, the direction of my displacement. They're 0 degrees from each other. But again, you don't need to type that. Okay, there's nothing here that's at an angle. If the entirety of your force is parallel to the direction of your displacement, that just means all of it is going towards doing work instead of some fraction of it. So I'm really just multiplying by 1, but I don't really have to worry about this unless I have a force that's being applied at an angle where some component of it is responsible, but not here. So I'm just going to multiply 260 times 20. And when I do that, I get 5,200. So that is his work done by his pushing force is 5,200 newtons. Now friction, again, I could calculate frictional force if they gave me some other information, like a coefficient of friction. However, they didn't. But what they did give me were these two words, constant velocity. And if I see the words constant velocity, I know now that the amount of force here from the push is equal to the amount of force here from the friction. And if those forces are equal and opposite, well, then the work done is equal and opposite because it's still going 20 meters. This is the work done by the pushing force, and the work done by friction is negative 5,200. It is equal and opposite, just like the forces are. This is question number 10. It says, a skateboarder pushes herself toward the right. Let's say we can ignore the effects of friction and air resistance. If she goes 140 meters while being pushed with a force of 440 newtons, how much work is done by the skater? Okay, and so again, work is force times displacement. There's no mention of an angle here, so I'm not going to worry about it. I know she's pushing herself forward, and so we are just going to assume that our angle here is completely parallel to the direction of her displacement, since it doesn't tell us otherwise. And so we're just going to take her force, we're going to multiply it by her displacement. In this case, that's going to be 440 times 140, and again, those are the numbers from the question. And when we multiply those, we get 61,600. And again, work is in units of joules. This is question number 11 on 601.1. It says a weightlifter lifts the sets of weights a vertical distance of 1.2 meters. If a constant net force of 380 newtons is exerted on the weights, what is the net work done on the weights? Again, you're just going to multiply force times displacement. Okay, they gave us the net force, therefore we can find the net work. We just use that net force, that 380 newtons. And we're going to multiply it by the displacement, 1.2 meters. That's force times displacement. That gives us our work, in this case 456, and again our unit is joules, capital J. Question number 12, 601.1 says, a kid pulls their red wagon down the street with a force of 93 newtons. Friction is 32 newtons. If the kid pulls the wagon for a distance of 40 meters, what is the net work done on the red wagon? So again, here they're giving us a couple of different pieces of information. I'm going to go ahead and draw a picture. Okay, so here's going to be my free body diagram for my wagon. I'm going to say that the kid is pulling it this way. The force of the pull, again, is, I'm going to call this my applied force, is 93 newtons. I know that there is an opposing force of friction of 32 newtons. And again, I know I'm going to have Fn and Fg, and that these are going to be equal and opposite to each other. Okay, now could I find the values of this? Not with the information I have, actually. Okay, I don't know Fn or Fg. They didn't give me a mass, so I can't even get numbers for those, but I don't need them. Okay, if I want to determine the net work being done, I just need the net force multiplied by the distance. Well, in this case, they gave me two different forces. However, when I draw them, I can see how I can find the net force. We've done this in a couple of our units now, but if I have 93 newtons going one way and 32 newtons going the other way, again, remember, net force is the sum of your forces. In this case, that net force is going to be in the x direction because, again, these are going to cancel. And so my net force is the sum of my forces. That's going to be 93 newtons plus 32 newtons. But again, forces are vectors. You have to keep in mind this isn't positive 32. It's negative 32. So when I add it, I'm really subtracting. 93 plus negative 32 is the same thing as 93 minus 32. So let's go ahead and figure out what that is. 93 minus 32 is going to give me 61. So my net force is going to be 61 newtons in the positive direction, which I defined as being to the right. That's not my answer. That is my net force. I can use this net force, F net, to find the net work. Okay, so again, work, or net work in this case, is going to be my net force times my displacement. Okay, well, I just found my net force to be 61. My displacement is 40 meters. It's in the question. And so if I multiply those two things together, that will give me the net work being done on the wagon. 61 times 40 is 2,440. And again, work is in units of joules. Question 13 on 601.1 says, you pull your friend in a sled with a constant force of 118 newtons at the angle shown above. You pull for a distance of 49 meters. How much work did you do? All right, so here is a situation where we have an angle. And when you have somebody pulling at an angle, only a portion of their force is going to be parallel to the displacement. And that portion is the only portion responsible for doing work on, in this case, the sled. Okay, so we can redraw this triangle. Okay, I know that, here's my right angle. I know that I have 118 newtons that they're applying, and so again, that's at an angle though. And again, this sled ultimately goes this way. Okay, the direction of displacement is along the ground, and so this component is the only component that is going to be doing work. This component not doing work. Okay, this vertical piece, don't care. All I care about is the horizontal component, so that force that's in the x direction. And again, I know how to find that because we also have an angle here of 30 degrees. So I know that I can find this with some trig. This side is adjacent to my angle, and so if I want to find the adjacent side and I have the hypotenuse and the angle, that's when we use, again, we go back to SOHCAHTOA, but it's the CA in SOHCAHTOA, adjacent over hypotenuse. So we say that the cosine of 30 degrees is equal to, the adjacent side is fx, that's what I need to find, that's the component I need, over the hypotenuse, which is 118. Okay, and so that ends up being, fx ends up being equal to 118 times cosine of 30 degrees. Again, when you go to enter something like this in your calculator, you do need to make sure that you're in degree mode in order to get the right answer. I already am, but 118 times cosine of 30 is going to give me a component of my force of 102.191 newtons. So that's the only part of the force that does work. Even though they're pulling with 118 newtons, some of it isn't doing any work. Some of it is lifting, although it doesn't lift it off the ground, there's no displacement, but some of it is an upward component. And so this is the only component that is parallel to the displacement. The displacement, again, is 49 meters. That's in the question. This is the component of the force that I get to use. If I want to solve for the work, I get to use that component of force, 100, oops, I put 120, sorry, 102, let me rewrite that, 102.191 191 times the displacement 49. Okay, and so I can take my answer and multiply by 49, and I get 5,007.36 if I round it to 2 decimal places. Again, you'll notice I did not round until the very end. Rounding earlier could throw off your answer in my open math. I do want to point out that we will get the same answer doing it this way or by using that dot product equation, the one that I've been writing out. Work is force times displacement times cosine of the angle theta. Again, if you use this equation, you just get to use the force from the question, because here's your cosine theta. That is this piece right here. It's just building it into the problem. But let me show you. 118 times 49 times cosine 30 degrees. Again, we can use this equation. There's the force from the question, 118. There's the displacement from the question, 49. There's the angle from the question. If you plug it in like this all in one step, we're going to get the exact same answer that we've already typed in. But let's go ahead and show you. 118 times 49 times cosine 30. And there it is again. Exactly the same thing. Okay, so you can do it either way. You can start by solving for the component and then use that component with the displacement, or you can just use that dot product equation that you learned in class. All right, here is another one at an angle. Let's get some fresh paper. It says, an applied force of 93 newtons is applied at a 27-degree angle. As a result, the box moves 10 meters to the right. How much work is done by that applied force? So again, same idea. This force is at an angle. Okay, when I look at this, this is where the force is. That angle is 27 degrees, it says so in the question. Okay, so this 93 newtons, only a portion of it is responsible for doing work. I can find that portion using trig. Okay, or I can go straight to my equation and use that dot product equation, F times delta x times cosine theta. And it's the same process. Either way, we get the same answer. Okay, so I'm going to take that 93 newtons. I'm going to multiply it by my 10 meters of displacement, and I'm going to multiply it by cosine of my angle. And again, my angle here, sorry, instead of writing theta, I need to write 27. Okay, but again, it's really these two. You're doing 93 times cosine 27. That's getting you this component, and then you're multiplying it by the displacement. So you can do it in steps, or you can do it all at once with this equation. 93 times 10 times cosine 27 gives us this. 828.64. My units again for work are joules. Question 15. If you lift a 1.2 kilogram textbook from the floor to a height of 1.3 meters, what is its change in energy? Okay, again, work is change in energy. So if we can find the work, we can find the change in energy. And again, work is equal to force times displacement, so long as that force is in the same direction as that displacement or parallel to it, same or opposite. Again, if it's at an angle, we multiply by cosine 30, or sorry, cosine theta. So again, I don't see an angle here. This is a situation where we have somebody that is lifting an object. Okay, and so they're going to lift, the force they're applying is upward, the displacement is also upwards. So they're in the same direction as one another. You're welcome to multiply by cosine of 0 degrees, but doing so, of course, will just be the same thing as multiplying by 1. Cosine of 0 is 1. Okay, so we just need to figure out what force they would have to use here to lift this. If you're trying to lift something, the force that you're applying needs to be equal to the weight of that object. And so although they didn't tell us the weight, we can calculate it. Weight is mass times gravitational acceleration. The mass is 1.2, gravity on Earth is 9.8. And so we can multiply 1.2 times 9.8. And that tells us that this is the amount of force you would have to use in order to lift that book. Okay, so when I go back to my equation, work is equal to, here's my force, 11.76 times the displacement. They're trying to lift it to a height of 1.3 meters. And so all I'm going to do to find my answer is I'm going to multiply this times 1.3, and that gives me the change in energy, or really the work done on this is 15.288, which is changing the energy of that book. If it is lifted at constant velocity, what force was used to lift it that distance? Again, that's just going to be the force due to that gravitational field strength. That's the weight. We already calculated it. It's 11.76. And again, forces are in newtons. How much work did it take? I feel like we're answering the same question over and over again because we've already answered it. Change in energy is work, so the work is still the same value we put for the first question, 15.288. And again, it's in joules. If I, with my hand underneath the textbook, carry it 3 meters to the left, how much work did I do? Again, in this situation, it's talking about you're holding something upwards, so you have to support the weight of it with a force. However, the displacement in this example is talking about going this way. These are perpendicular to each other. Again, if no component of your force is in the same direction as your displacement, you don't do any work. Okay, and so again, you would have 0 joules of work in that case. Number 16, the work you do when pushing a cart for a given distance while applying half as much force is. Okay, so again, work is force times displacement. If you only use half as much force, then you would expect your work to be half as much. They do have a directly proportional relationship with one another. And again, if you're not sure, put in some fake numbers. If work is force times displacement and you want to just say, okay, well, initially, you know, I applied 10 newtons of force to cause a displacement of 10 meters. So that'd be 100 joules of work. And then it says if you have half as much force, okay, well now I'm only going to use 5. That's half as much, but I still push at the same distance. Again, you can see here the factor. Plug in fake numbers if you don't know, but this is clearly half as much. Last question, number 17 says, Corey and Taylor both move identical boxes from the ground to the top of a ramp. Corey lifts his box vertically 3 meters from the ground up to the top of the ramp in 4 seconds, whereas Taylor pushes her box up the 6-meter long ramp in 8 seconds, which describes the work done by each person. Okay, I'm going to draw a picture to help us see this a little bit better. Okay, so this is a scenario where we have 2 people, and we had a picture kind of like this in our notes, both of them trying to get boxes to the top of this ramp. Okay, one of them is pushing their box up the ramp this way. That is Taylor. Corey, on the other hand, is lifting his straight up. Okay, so there's Corey and Taylor, what they're doing. They both start at the ground. Okay, and they're both going to end right here at the top. Okay, and so it asks about which describes the work done by each person. In both cases, and we talked about this in class, work is independent of the path taken. It does not matter how the box gets from the ground up here. In both cases, it gets from the ground up here. Okay, and so if that is the case, if you're moving something from the ground up a ladder, using a pulley, going up a ramp, whatever it may be, okay, if you're lifting the same amount of weight, you're working against gravity in both cases. Okay, and you're working against gravity to get it to the same height. And so in both cases, they will have the same amount of work so long as everything else is equal, so long as it's the same box, which it says it is, identical boxes, then we would say they do the same amount. Corey does the same amount of work as Taylor. All right, but that is how you do the questions here. So again, if you have questions, make sure that you ask in class.